This video will show an example of a two-tailed beta test. So let's suppose we have a null hypothesis of 12.3, and then our alternative is not equal to 12.3, so automatically that sets up a two-tailed test. Sigma 6.8, we're going to do it at a 0.01 alpha level with n equal 100, and then when we get to part 2, we're going to do it for a true mean of 11.3. Now, a couple things when dealing with two-tailed compared to one-tailed. As you know, when you set up your hypothesis test, your sigma level of 0.01 has to be split between these two-tailed, so they're each going to be 0.005. So our first step in any beta problem, of course, is finding that critical x bar value. To define the critical x bar value, we have to use the critical values for our particular test. So when we look up our critical values for this test, we need to use the 0.005. So if you quickly just go to your formula, and remember, you can find those quick values here at the end of your t-table. So 0.005 is going to give us critical values of 2.576. When you put them on your chart, remember, draw pictures. Pictures always help you visualize what's going on and help you figure out what that next step is. So we have critical values of negative 2.576, 75. Depending on where you get them from, it could be a 75 or a 76. And positive 2.575. I'm going to use the 75 for these. That should not make that much of a difference, even in MATLAB where it is a little sensitive to rounding. So step one, of course, is we need to find our critical x bars. And to do that, you use your, wrong one, let me erase that, your basic formula, your hypothesis formula, x bar minus mu over sigma over square root of n. But this time, our critical values are going to go in for z. We're going to use those critical values. And because it's two-tailed, you've guessed it, you've got two different critical x bars, a and b. So for the first one, I'm going to use the negative 2.575. X bar is what we're looking for, so that stays x bar. For step one, you use the mean in the original hypothesis, what we believe to be true, that 12.3, not the true mean yet. We get to that in step 2. Over sigma was 6.8 over square root of 100. Remember, this will give us that mean that represents the cutoff for rejecting or not rejecting. The other thing you want to keep in mind before going forward is, you know, your beta, your type 2 error, of course, is your probability of not rejecting. So ultimately, when you look at a two-tailed test, where is that area of not rejecting? It's always going to be between those two critical values. So ultimately, when we go to find beta at the end, it's going to be the area in between. So that's just something also to keep in mind when you get started. So we have to go ahead and find those two values. And of course, the other one is we use the positive 2.575 equals x bar. And the only thing that changes is that negative and positive for our critical value. Okay. You would go ahead and work those out. And I'll leave the math to you, but when I did it, I got this x bar equaling 10.55 and this x bar. So I'm going to call this one x bar 1 and this one x bar 2. And this x bar equaling 14.05 about. Okay, so of course, like I said, I'll leave the math for you. Obviously, do the denominator first, figure out 6.8 divided by square root of 100, which is just 10. 6.8 divided by 10, that's pretty easy to figure out. And then multiply it by the negative 2.575 and then add, in this case, and figure out those two X bar values. Now, for step 2, we actually need to find beta. Again, we're going to have 2 parts to our curve here. So, you know, this is something you kind of went over back in stat 1. You can draw a curve that is called unstandardized, and it has the actual mean and everything. When you get to step 2, you're going to use that true mean of 11.3. That was your true mean that we're testing it against. So, okay, what are our values, our X bars in the original problem? If we were to reject, they ended up being what, 10.55, which is, now these are not even. I did not draw this to scale at all. And 14.05. Clearly, this bar would be much further over than this one. But keep in mind also, sometimes when you do this, you won't even be centered around that mean. Sometimes you'll do a two-tailed test and both bars would be to the left, or both critical values would be to the right. It's fine. You're still looking for the area between those two numbers. Keep that in mind. Ultimately, we want to find this area. That's our beta. Okay, so to do that, we go through what we call the standardization process. And I apologize if my dogs start barking now, but I'm going to keep going. So you have to standardize. Start with the 10.55. We need to know, hey, what is the z-score that 10.55 represents in this problem? What is the standard score for that one? And what is the standard score for 14.05? So to do that, Z1 is going to be, use that 10.55 as your X bar, because it is an X bar. It's one of our critical X bar values. But this time we're using that true mean of 11.3. And of course your 6.8 divided by square root of 100, which should just be 0.68 divided by square root of 100. Do the math and you should get a negative 1.10 here. And for X bar 2, same thing, but now use the 14.05 minus 11.3 over. And you get approximately, did the math really quick, so some of these numbers could be off a little bit. I apologize for that. 4.04. So if I were to draw this curve unstandardized, you know, we can certainly get a better idea of what it would look like. 0 would be in the middle. My 11.3 goes to 0 when we standardize it. So we have negative 1.1 might be right about here. And, you know, 4.044 would be clearly off pretty far to the right-hand side. But this is still our beta. Okay. Now, this again goes back to what you learned in chapter 6 and stat 1 is how do you get the area between those two z-scores? Well, you find the area, the larger one, and subtract it from the other one. Well, this one is so big, so let's go to what is the area? Hold on. To the left of 4.044. So that would be a curve with just the 4.044 in it, and it would be this huge area. Well, you'll note real quick when you look at your curve. Hold on. I wanted to find our z-table. There's a z-table. If you try to find it's not even on there. Anything at 3.9 or greater, you will see on your z curve, we're just going to use a 1. And it says for any z value greater than 3.9, use 1 because it's so close to 1. We're just going to use it with the entire area. So this is going to be area is 1. Okay. Now, then you want the area to the left of negative 1.10, because that's going to represent this area. And if you recall, what you do is take the area to the left of the 4.044 and subtract then the area to the left of the negative 1.10. So we need the area to the left of negative 1.10. So we go back to our Z chart and we look up negative 1.10, which is just going to be right here. Negative 1.10 is the area is going to be 0.1357. So go back. This is the area, 0.1357. So it's going to be 1 minus 0.1357. And I don't have my, it comes to approximately 0.864. Approximately, rounded to 3 decimal places, which is what you normally have to do anyway. Comes to approximately 0.864. So beta is the area of 0.864, or 86.4% chance of making a type 2 error. And then, of course, your power. What is the power of this test? It's 1 minus beta, which is 1 minus 0.864. That's going to be 0.136. So your power, it's not a very powerful test. The reason being, of course, when you think about it from the very beginning, that 11.3 is really far off from our true mean of a pause. Something's wrong. That 11.3 seems really far off from the 12.3. So you would think your beta would actually be a little smaller and your power would be larger. But the problem with this here is we have such a large standard deviation that if the true mean was 11.3, you'd still have a hard time of rejecting this hypothesis. Because again, it doesn't seem like it's very close, but there's such a large standard deviation in this problem that it is likely that even though the true mean's 11.3, we could get a sample that would cause us not to reject. So that's why this is not a very powerful test.